Right, so the process that we talked about earlier was really focusing around multiple systems, right? So we drew multiple free body diagrams. We had multiple equations with multiple unknowns, right? This new system or this new process is going to we're going to treat the Atwood machine as a single system, okay? And if you remember, the red flag that I threw up for you guys is at some point in time when you do Atwood machines, you're going to divide by total mass. You're going to see that here. Okay, this is where it kind of comes from. All right, and so we've talked about Atwood machines, right? We've defined what Atwood machines were before. Where am I? Pen's not working. Hold on. Oh. That's why a USB popped up. There you go. All right, perfect. All right, so an Atwood machine, right? We talked about what these were. It is a basic physics laboratory device often used to show or to demonstrate basic principles of dynamics and acceleration. Okay. If you actually look at my board there, I've got like things that I need to make sure I hit or do for you guys. And you see the top thing that I wrote up there today was Atwood machine demos. And what I'm going to do is I'm going to put on the YouTube channel just some demonstrations using and showing Atwood machines. Okay. I also, am I muted or something? What's up? Oh yeah, sorry. I did that earlier too and I forgot to share my screen. There we go. All right. So, and so that's what I'm going to do. I'm going to make some, demos, and I'll take some data to show you how this works out and do some predictive things. But typically they involve a pulley, a string, and a system of masses. Right. Now the system of masses, and I don't know if I threw this off on the test, but one of the questions on the test had 3 masses, right? 2 on one side, 1 on the other. Okay. But again, if you follow through our process of draw, sum, solve, and in that case, if you follow through for each mass, you would have 3 free body diagrams, 3 equations, 3 unknowns, right? And that will allow you to kind of solve through. All right. So the most basic Atwood machine, right, is just simply 2 masses over a pulley connected by a string, right? Where one mass, right, we have mass 1, mass 2, right? Where mass 1, for example, will be greater than mass 2. Why does that have to happen? Because if they're equal, guess what happens?
Nothing.
Nothing, right? Nothing happens if the 2 masses are equal, okay? Now, how do we change that up? Well, then we take the masses and we put one on a table, right, and one hanging off the table, right? We call that a modified Atwood machine, okay? And then how do we change that up even further? Now we put the one that's on a table goes onto an incline, right? So those are the 3 versions of Atwood machines that you can have. The basic one, which is the 2 masses over a single pulley, 1 on a table, 1 hanging off, and then 1 on an inclined plane and the other hanging off, okay? We always assume massless frictionless string, massless frictionless pulley, okay? Because that leads to the keys to solving these problems, right? So these 2 keys are the most important things that have to happen or for you to be able to really solve these problems. The first key is that you understand that the tension in the string and the acceleration of the system, they're constant, which means I don't have like a separate acceleration for mass 1 versus mass 2. The accelerations are the same. Same thing with tensions. The only time the tension is not necessarily constant is when you have that second mass hanging off one side of like the basic one here. Okay? Like what you saw in the test, which you actually see on the back of, or page 2 of the PDF file. And the last question on the back here. Right? So you always make the assumption that the tension and acceleration is constant. Now, when I do the demos and I collect the data, is it going to be constant? Maybe not, because there's friction involved, right? I'll use the fishing line, right, to do this. I'll try to figure out a way to try to keep my friction as minimal as I can for some of the ones that I'll do for modified Atwood machines. Okay, but we're always going to make the assumption that the tension and the acceleration are constant. The second key to solving these problems is the positive direction, right? Choosing the correct positive direction. And because of the pulley, the positive direction changes, okay? How do we choose the positive direction? Well, we want to go in the direction of the motion. Right? So if I have my basic Atwood machine, right, my two masses over the pulley, it's going to move in the direction of the larger mass. Right? That's how it works. Now, in that case, it would accelerate in the direction of the larger mass, but it doesn't necessarily have to move, right? Or it doesn't have to, those two, the motion, right, the direction of motion and the direction of acceleration, don't necessarily have to be the same. You're going to see that in the fifth example, the inclined plane with friction, okay? And that's because of what happens, you know, with some of the factors that are involved with it, right? And so here's the new process, right? Putting new in quotations because it's not necessarily a new thing, it's just a different way to look at these problems. So basically what I've done is we did the multiple system process, right? Some of you guys got it pretty well, some of you guys didn't do so well with it. So again, I tell you, I'm reflective in my teaching. So let's do the single system, right? Let's treat this as a single system, okay? So the first thing you're going to do is identify the two masses as the entire system, right? And if you need to, you can circle it. Here's my system, right? So when I draw a free body diagram, I'm just going to treat essentially, or take those objects and say this big mass is equivalent to those objects, right? So if I have like a 2 kilogram mass and a 3 kilogram mass, okay, I'm going to say, okay, I can take a 5 kilogram mass, drop it with these two forces, and it would be the same effect as if I had a 2 kilogram and a 3 kilogram separately, okay? But if you look at steps 2, 3, and 4, that's our basic process, right? Draw, sum, solve. There it is, right? Our 3 steps. So step 2, draw a free body diagram with the forces that are trying to pull the system. Now, the pulling means the tensions in the ropes or the strings that we often solve for. When you have a system that is acting by itself, the tensions are negligible. We don't have to worry about them because they're internal to the system. And if you remember, one of the first things that we did when we started Newton's laws is that we said anything that was inside our system we didn't worry about in our force calculations. We were just looking for the things that want to try to accelerate the object. And tension doesn't want to accelerate the masses here. Okay. Oftentimes, what is accelerating the object?
Gravity.
Which is, what's the force of gravity called?
Weight.
But it's the weight, right? So the weight's trying to pull it. What else is trying to pull it? No. Because tension's inside the system.
Oh, right.
What's the other big force
Normal force. Friction.
Friction. So, the weight of the object, one object is trying to pull it while the friction is trying to pull it the other way. Okay? Now, step 3, sum the forces and set equal to m times a. Guys, because this is a single system problem now we're turning into, it basically looks like a basic Newton's second law question. Like how much force is exerted on an object going this fast, having this mass? What's the acceleration of an object that has this much force on it and it has this much mass? That's what it just turns into. Okay? And then we're going to solve for the acceleration, and this acceleration is for the system, right? Which means, if you remember, our first key was you understand that the tension and the acceleration is constant. So when I find this acceleration, it's the acceleration of all objects in the system. Okay? Because the system is accelerating at that rate. Which means the individual objects accelerate at that rate. Think about you sitting in a car. Your car accelerates. It's not that you now all of a sudden accelerate at a different rate. Because if that happened, you'd either go flying through the windshield or you'd go out the back. Right? If you accelerated faster than the car you're sitting in, you're going through the windshield, right? Because you want to go quicker that way. If you go slower, what happens? You'll go through the back because you don't want to move, right? You're not going to accelerate as fast as the car. But if you're in the car, guess what? You're part of the system, which means you're accelerating at the same rate. That's what happens here. If this accelerates at 2 meters per second squared, that accelerates at 2 meters per second squared. Everybody got that? Good. And then step 5, because oftentimes these questions are find the acceleration, find the tension. Now you find the tension. How do you find the tension? Well, you find the one that is the simplest object. The simplest object is basically the one that has the least amount of forces acting on it. Or the least complicated forces acting on it. You'll see when we do the inclined plane, you'll know which one to deal with, okay? If you go to our diagrams here of our 3 Atwood machines, for the basic one, choose either one. I would probably choose this one because this will accelerate downward, this will accelerate upward, right? Which means then my tension is positive and my algebra just becomes adding a single term over to the other side. Right? Because if I do this when my tension is negative, which means that I have to add it, then subtract. Right? So if you want to minimize your algebra, choose the smaller of the 2 objects, right? The one that's going to accelerate up. Okay, now if we're on a table, you got to look at if there's friction involved or friction is not involved, right? If there's no friction, do this one. Right, that would be your simplest one because the only force pulling that object is tension. Right, if there's friction involved, you would have friction opposing, which means your algebra, it doesn't become hard, right? It's not like all of a sudden it goes from like algebra to differential equations. It just goes from like having to just simply divide by mass to having to add and subtract stuff, okay? If you have friction involved, do this one. Right? So we do that. On the inclined plane, again, I would probably do the hanging mass. Regardless if there's friction or no friction. I would just do the hanging mass because of the inclined nature of the one that's on the inclined plane. If you don't want trig involved, do the one that's hanging. But here's the thing. If you choose to do the other ones that I did in circle, you're going to get the same answers. Right? You're going to get whatever answers that you're supposed to get. Okay? So the first two I'm going to do, pretty slow, just so you guys can see how this works, right? And then the next 4, I'm going to go at a little bit different pace. Everybody got that? Okay, good. Virtual friends, if you guys have questions, go ahead and make sure you add them in the chat. I'm going to blow up my chat here so I can see it. I could also use the iPad that the school got us to monitor that chat as well, but I'm lazy. All right, so the basic Atwood machine, right? Here we have two masses, M1 and M2. They're hanging by a massive string from a frictionless pulley. M1 is greater than M2. That's important to know because now we can identify which direction this is going to accelerate, right, or move. Determine the acceleration of the two masses when released from rest. And remember to choose the positive direction to be the direction that the mass will accelerate. Really, I copy and pasted this. This shouldn't necessarily be where it accelerates, but it should be the direction of the motion. Okay? So we know this. If I let this system go, this is what's going to happen because M1 is greater than M2, right? M1 is going to drop down, M2 is going to go flying up. Okay? And that's important. So here's my system, right? Everything inside that circle is representative of my system. So note what happens to the tensions. They now become internal, right? Because where are they located in my circle? Inside, right? So you see how this internal part works? But what is actually trying to pull these masses? Right. Gravity's trying to pull both of them, right? Gravity's going to pull M1 this way, right? Right? And then gravity wants to pull M2 this way. Now remember, this is where gravity wants to pull, not the way they're actually going to move, right? Because M2 is going to move up. Right, in the grand scheme of things here, okay? So I've identified the forces. I have my positive directions, right? So now let's translate that into a single system. So here's my single system. This block has a total mass of whatever, okay? What forces are acting on my system?
Gravity and tension.
Is tension acting on my system?
Wait, well, it's a force involved, but it's not acting on it.
It's a force involved, but is it trying to pull my objects? Trying to pull my masses? No. Right?
No.
Another way to think about it, where are the strings located in my circle? Are they outside or inside?
Inside.
They're inside. Anything inside my circle doesn't matter. These are poking out of my circle. Right, this one, even FG2 doesn't really poke out, but it wants to come out of my circle there, right? And so that means that it's trying to pull it. This is where it gets confusing. Like first period was asking these questions like, why'd you put that force this way versus that way and so forth, okay? Note positive directions here, okay? So in actuality, which way does FG1 act? Positive or negative? Not negative, but positive. Because it's pulling it down. Which way is this block accelerating or moving? Down. And that's our positive direction. On my box over here, FG1 actually points up. When you come over to your single system free body diagram, you're conventional, right? Your positive X is to the right and your positive Y is up. Okay? Over on our basic diagram or our diagram off to the right there, it's confusing, right? That's why I want to go kind of a little bit slow through this one and the next one so that you guys see how this works, okay? So which way does FG2 act? Positive or negative? Right? Because remember, for mass 2, our positive direction was which way? It was up. FG2 points down. So that means it's trying to pull it downward in the negative direction. Does someone have the notes packet from where we did this? I know no one like 2 people third period had it, and there's like 14 kids in that class. Go to the page, go to the section on Atwood machines. I think I did this one in here. Just yeah. All right, good. Because guess what? This is the first example of Atwood machines in the notes packet, basically. Did we put any numbers in that one, or we just?
No.
Right, okay, so you're gonna see the comparison between the two, right? Two systems versus one system. In fact, what I'm gonna do is I'm gonna fill this one out using the one system, but I'm gonna fill it out again using two systems, right, multiple systems, and you're gonna see they're the same, right? The answers are gonna be the same. It's not gonna be like a miraculous change that one system versus two systems gives me two different answers, okay? So now we sum the forces, right? We drew our free body diagram. Now let's sum the forces. Sum of the forces is equal to the total mass times the acceleration. Because remember, we're going to total the mass because we circled everything, right? That becomes our system. And what was the big red flag I told you about Atwood machines?
Divide by total mass.
You're going to divide by total mass.
Find the acceleration.
Right? There it is right there. Okay? And so what forces do we have acting? We've got FG1 up. We have FG2 down. And it's going to be equal to M times A. And we're looking for acceleration. We're going to have FG1 minus FG2 over MT. And now we're going to plug in like, M1, M2, and so forth and simplify, right? And so FG is M times G. So this is going to be M1G minus M2G. And it's going to be M1, total mass is M1 plus M2. And what I can do here is, right, G is the same, so I can factor it out. So acceleration is going to be G times M1 minus M2 over M1 plus M2. Look at that first example in the section on Atwood machines from the last notes packet. What did we get for the acceleration of the system?
G, big M minus small m, big M plus small m.
Ding, 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 ding. There it is right there. Now, the difference was we said big M and small m, right? But what did we say about mass 1 and mass 2? Mass 1 was greater than mass 2, right? When it's big M and small m, big M is bigger than, right? So there it is right there. So there's our acceleration. This one doesn't ask for the tension, but at this point in time, now you go back and say, okay, now I'm just going to look at one of my blocks and find the tension based off of that. Right? So, because now I need tension to be an external force. How do I do it? Now I just look at a single block. Okay, so, and I would do, when I want to find tension, I would do M2, because that puts tension positive. That just makes the algebra easier. I don't have to do two steps of my algebra. I just have to do one step of subtracting M2G over. Right? And for the most part in these questions, for the hanging block, tension is going to be the mass of the hanging block times G minus A. That's going to be the tension in for the most part. Okay, and so you can you can, if you have the, because on the notes packet it did say to find the tension, right? Or did we just do it?
Yes.
It did say find tension, and so you're going to get like here you get M2 times G minus this right there, right? Because that would be the acceleration. Okay, and then you can, if you really want to, you can factor out a G and be like mg times 1 minus that. You can do it for the other block too if you want, but your algebra is just going to be like add then subtract. Okay. So if you got more practice with this, do you think it'd be a little bit easier to do one system? At least to find the acceleration, right? All right, so let's look at the, whoa. Everything went wrong on that. All right, so let's look at what happens now when we have the Atwood machine on a table. Okay. In fact, this question and the next question both were old AP multiple choice questions. Okay.
How many questions are usually on each exam?
The multiple choice section on the AP Physics 1 test is 50 questions. And then there's 5 free response questions.
And how long do we have to do all those?
Hour and a half for both sections. Like you have an hour and a half for multiple choice, hour and a half for free response. But you have to understand, a lot of the multiple choice questions are conceptual based where they should take you 30 seconds, right? Even if it's a question like identify the free body diagram of the situation that's happening. That should just be like, oh, boom, 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 done, right? Which of the following is a vector? Done, right? Like, so you need to save your time, right? Because it's a time test. You need to do the easy ones, right, quickly so you can save time on the quote unquote harder ones, or the ones that you perceive to be harder. That's just a basic test taking strategy, like the SAT, right? SAT, PSAT. Typically, all the easier questions are at the beginning. So if it's a 45-minute section, those like 5 to 10 questions should take you no more than 5 minutes, right? So if you go to like these centers that do test prep, that's what they're going to tell you. They're going to tell you the first 5 to 10 questions on the section, on the SAT, PSAT, should not take you 20 minutes. It should take you like 5 minutes tops. And this way you got the bulk of your section should be done on the medium questions. And if you get the hard questions, good. If not, oh well. All right. All right. So here's my system, my 2 blocks, right? So I got a 3M block. I got an M block. 3M's on the table it's on a friction table or frictionless table. M is hanging off. Basically, it's asking us what is the acceleration and what is the tension and the strength. Now, on the AP test, this just asks for the acceleration. I added in the tension piece, okay? And so here's my system. What is the only force that is trying to pull this system? Which weight?
Weight of the first one. Yeah.
What are you saying?
Second one, sorry.
Hanging.
The hanging, right?
Just it. Weight of.
All right, so the weight of the hanging block. Right? Nothing else is trying to pull it because we have a frictionless surface. Right? And so there's my free body diagram, basically. All I have to do is now replace the circle with my box, right? And say, okay, this is total mass. Because what's the giant red flag again with Atwood machines? Divide by total mass. Okay? Maybe that'll be my saying, right? There's teachers that are like, so the AP videos I'm saving as to help us with review when we get back from our December break. One of the teachers says, well, look at that, physics works, right? That's his saying. He says it almost every video. I don't know, mine probably needs to be something to do with like the giant red flag, right? Because there are red flags for all these questions that should go up, right? When you say, oh, Atwood machine, I know I'm going to be divided by total mass, which means if this is a multiple choice question and you don't have total mass in the denominator, gone, right? As long as you're looking for acceleration, it's just automatically eliminated. Okay? Now, I do want to point out here, the 3M block wants to go this way, right? The M block wants to go down, but understand this, that motion is horizontal. Okay? I know it's weird because no, Ms. Solana, you're wrong in saying that this is horizontal motion because this is vertical. Caleb's doing it. Caleb did it, right? Free body diagram, or here's my coordinate system. As I travel, right, what happens? I have to go through the pulley. And so if my thumb is my positive X direction, when I travel through the pulley, which way is my positive X direction point now? Down. Everybody got that? So that's why this motion is actually horizontal, even though the hanging mass wants to move vertically. physics-wise, it's horizontal, right? And so when I draw my free body diagram, when we did, right, the hanging one up here, we did everything vertical. We're accelerating, right, in the horizontal direction here. Right? There's only one force acting because there's no friction. And so now this just becomes like the first example on the previous, right, the other special topic, the service one, where we said it's basically just, F over m define acceleration. So sum of the forces is equal to ma. And what's the only force acting? Fg2, right, equals mass times acceleration. So Zoe asked for you guys in the room, for any Atwood machine problem, does it matter if we solve for the single system or two systems? No, I'm just giving you guys more options, really. Okay, just kind of giving you more tools in your toolbox to solve these questions. Does it work the same for other modified Atwood machines? Well, we're doing them. Yes, it does. This method of one system, right, always works. Okay, because, again, that giant red flag was you divide by total mass. If I have multiple objects, well, my total mass just gets bigger, okay? And so to find the acceleration, we're just going to do, it's going to be Fg2 over mt, right, over total mass. So Fg2, right, so it's going to be mg over, right, total mass, so 3m plus m, which 3m plus m is 4m, right? But this m is just a general m, right? So what happens to this? Goes away. And so your acceleration is going to be 1/4 g. Now, when this was the question, right, on the AP test was, what is the acceleration? Okay, I added in the tension, and you don't have to plug in g because this was an older multiple choice question, which means on that particular test they didn't allow the calculator on the multiple choice section. Like when I took it way back in '95, we didn't have calculator on the multiple choice section. Okay, we only were allowed the calculator on the free response section. Okay, so when you see questions like this, and this is the classic tell, you see the very basic picture, right? It's not really detailed, right? It's a box on a line, hanging off a line, right? Another box is hanging off of another line, right? It's not like this nice, pretty looking picture, okay? That tells you it was an older question, which means your answers are going to be looking like this relationship type thing, okay? All right, so there's our acceleration. Now let's find the tension. So again, no friction. Recommendation is to use this one to find the tension, right? It's not wrong to use the hanging mass. You just would have an extra force there, right, to worry about. Here, we only have one force acting, right? So there's three forces acting, but one that we care about because it's a frictionless surface, right? Remember when we talked about surfaces, if it's frictionless, we don't worry about the vertical pieces, right? We only worry about the horizontal piece. And what force is that? Tension. So tension is going to be equal to m times a, right? What was the mass? 3m. What was our acceleration? 1/4 of gravity, or g over 4. So what is the tension equal?
3/4 mass times gravity.
Now, if you really wanted to check me and say that if you use the other one, you get the same answer, go for it. Right? You would say it'd be Fg2 minus T equals Ma, right? And you would add and subtract. You end up with Mg minus 1/4 Mg. 1/4, or mg is 4/4, right? So it's 4 minus 1/4, which is 3/4. So 3/4 the weight would be the tension in the string. Okay, everybody got that? All right. Virtual world, you guys, if you continue to have questions, please ask, okay? Now we're going to go a little bit faster, right? I'll slow down on the friction angled one, inclined plane, because that one, if you don't slow down on that one, you're going to get all messed up, okay? All right, so what's my system going to be in this question? Oh, so I got 2 blocks. One, the 4 kilogram block on the surface, 2 kilogram block hanging, okay? And we're asked to find the minimum value of the coefficient of friction that will prevent the blocks from sliding. Anytime you see static friction, what's our acceleration?
0.
0. Static means not moving at all. Okay? My system, right? M1, M2. So what forces are trying to pull this system?
Weight of M2.
The weight of M2. And what else is trying to pull the system?
Friction of M1.
Everybody got that? It's good that you guys saw it right away. First and third period, it was like, wait, what? There's something else trying to pull us? Guys, friction tries to pull, right? Friction is trying to pull the M1 away from this situation, right? Because it doesn't want to move. Okay? So what does our free body diagram look like? We have a total mass, right? And so what happens? I've got, again, we're moving which direction? Horizontal. So we have positive, right? Because if this were to move, if I were to move friction, right, it would be like this, right? The block on the table wants to go to the right, the block down wants to go down, right, hanging wants to go down. So we got FG2, we have friction. These two should be about the same size, even if they may not look like it, because there's no acceleration, and we're talking about static friction. Okay, so now it just becomes, right, sum of the forces. But you guys understand, like, it's the same process. What were the 3 words for our Newton's laws? Draw, sum, solve, right? Draw. Now we're going to sum, right? Sum of the forces is equal to 0. And what forces do we have acting? We have Fg2 minus Fs equals 0. And now we have what? Fg2 equals Fs. But what does Fs equal? The static friction, what does that equal?
mg.
U times the normal force, right? So we do have to we have to worry about the vertical for M1. But what happens when we worry about the vertical for M1? What does Fn equal? Mg, right? So M1g. So that's so Fs, remember, friction is mu times the normal force, right? And so this over here becomes mu M1g, right? And so that's what I'm going to plug in. So I have M2g equals mu M1g. So what can I do with gravity? Right now we're just doing some algebra, right? Get rid of the g's, right? And so we have M2 equals mu M1. And we're solving this for mu. We're going to divide by what, Caleb? So you find that the minimum coefficient of static friction is the ratio of the masses hanging to table. Everybody got that? This is why if you put a larger mass hanging off the table, right, than what's on the table, it's going to go, right? It's going to accelerate. And so this asks us so we actually have to find this. So hanging is 2 kilograms, table is 4, right? So we're going to do 2 kilograms divided by 4 kilograms. So what's the minimum coefficient of friction? Half. So anything less than that, the object slides. Anything greater than that, the object is definitely not moving. 0.5 is kind of like the break-even point, right? This is where it happens for this scenario, right? If M2 goes bigger than M1, moves. In fact, the lab we did, right, it was the hand pulling the block. The other way to do this lab, determining coefficients of friction, is to actually set this up, and M2 actually becomes like a cup or something you can hang masses off of, and you just add masses in or on until it begins to move. And then you see the comparison between the two, right? I know how much is sitting on the table, I know how much is there. But you're going to do the same kind of, you're really going to do this, right? So you would plot, this is the graph that you would plot, right? Hanging mass to table mass, and the slope of that graph would be your coefficient of friction. All right, so far so good. So let me ask you this. And virtual word, you guys can type in the chat box. Is this easier or harder, do you feel, than the two systems? Easier? So with more practice, because Luke's like, with more practice, could you do this better than the other one? Probably. All right, so let's rock your world now, right? Let's put this stuff on an incline. No, the dreaded incline plane. Yes, love incline planes. In fact, we did these two problems, I think. I know we did, I'm pretty sure we did the second one here. Okay. So look in that.
I think we did something first.
This is the second one then. Is it the second one?
Yeah.
Yeah, so this is the one we did in the packet is the second question here, I think.
It's different numbers.
Or is it this one?
Attention, I need to be incorrect.
All right, well, so I got these questions from physicsclassroom.com.
Yeah, it's frictionless. So.
Oh, so it's the first one that we did.
Yeah.
Is it different numbers though?
Yeah, no, it's the same number. Oh, wait.
Same numbers? Okay.
It is, yeah.
So we got the 4,000 hanging and the 2,500 up on the surface?
Yes.
Okay. Good. So you can see, now you can look at the direct comparison between the two methods, right? Because this problem we did. Okay? So here's our system. And guys, I would recommend circling. See how I'm circling everything? Right? I would recommend circling. Like, here's my system. Boom. I know I got this giant mass, right? So here's my giant mass over here. Right? M total. Okay? What forces are trying to pull this system? Actually, let's do this. Which way would the system want to move? Which way would M1 want to move? Which way would M2 want to move?
And M2 would want to move down.
Right?
And down would be horizontal.
So, right, but so again, we're still working in the horizontal, right? So M2 wants to go down, M1 wants to go up the incline. Now, I'll tell you for the next one, right, it's going to be a little confusing because the system's actually going to accelerate down the incline because of how things work out, okay? But what forces do we have acting on our system?
FG2 and FG1.
Now, is it FG1 or is it a piece of FG1?
A piece.
Why is it a piece of FG1?
FG1X.
Right, because we're on an incline, right? Remember, anytime you have an incline, the weight is not the full weight, it's a piece of the weight. Okay? So here's my free body diagram. I have FG2 trying to pull it positive. And then I have FG1X trying to stop it, right? Trying to say, no, I don't want you to go. I don't want you to go. But we know this is going to accelerate in the way that we've shown because FG2 is greater than FG1, or excuse me, FG1X. If you don't believe me, do the quick calculation, right? This is 40,000 newtons of force. This is 12,500 newtons of force, right? Or, this here, FG1X is 12,500 newtons of force. Remember, FG1X is M1G sine theta, right? And the sine of 30 is a half. Okay? And so now we sum the forces, right? MA. And so what forces are we acting? FG2 minus FG1X equals M total A. Now what's the acceleration? FG2 minus FG1X over M total. Well, FG2 is mg. So M2g minus M1g sine theta. Over M1 plus M2. Now, something that you could do here, because now it's like, oh, now I got to plug all this in, I'm going to run out of room. Even off to the side here, right, you can just kind of like collect all these numbers together, right? You can say, okay, M2G or FG2, right, is just simply M times G, right? And then MG or FG1X it's 25, right, times 10 times sine 30, which is 12,500. Okay, you just kind of collect all this stuff to the side, right? Because now you don't have to like plug it all in to take up space. And then M1 plus M2 is 6,500. And so you would do 40,000 minus 12,500 over 6,500. So 40,000 minus 12,500 divided by 6,500. So you get an acceleration of 4.23 meters per second squared.
2,000, wait, 500, no, 12,000. Right? Wait.
On inclined planes, x goes to sine because of the angle. Right? Because we know the vertical angle versus the horizontal angle. Right? Did I do that right? I've done this problem 3 times today. You guys are going to quickly join the 69.4 list if I'm wrong. No, I'm not. All right. Now the tension, right? Again, recommendation, use this for your tension, right? Remember, you're looking for the simplest. The simplest could be the least complicated or the least amount of forces, right? Unless you want to bring in all this angle stuff, use the hanging mass. In fact, I showed you what it breaks down to be, right? M times G minus A. That's what it ends up being. And so this would be hanging, which is 4,000 times 10 minus 4.23. I think it ends up being something like 23,000. Yep, 23,000. Now, I took this question from physics classroom, okay? And the guy who does physics classroom likes to use 30 a lot because like sine of 30 is a half, cosine of 30 is root 3 over 2 or 0.8660. Like those are known values that all students should know, okay? Especially if you're taking any kind of basic trig course, as in like geometry, okay? Now let's see what happens when friction is involved. And I will tell you right now, this system wants to do this. Okay? One of the reasons why the heavier block is now on the incline. Okay? So,
Friction can oppose the force.
right, so here's what happens, right? If I look at my system, it's here, right? What forces do we have acting? Well, we've got FG1X wants to pull it down the incline, right? And you have two forces trying to bring it up the incline, right? You have FG2, and I'll draw it down here with it, but it's actually right here. But you also have the friction. Okay? And so when I draw that on my free body diagram, right? And so again, down the incline is going to be positive, right? So FG1X is going to be here, right? We're going in the direction of motion. I want to go down the incline. Friction is going to be negative, and so is FG2. And let's kind of collect some of this stuff together over there, because if we kind of plug in all the numbers, it would take up like the majority of that space, right? So FG1X is M1G sine theta, right? And so it's going to be 3,500 times 10 times sine 30, or 17,500. Okay. FG2 is M2G, which is going to equal, so it's just going to be 1,000 times 10, or 10,000. Okay, so we got that. And then this is the one that's going to be kind of the one that would take up the most space if I put it all out, right? This is going to be U M1G cosine theta. Now, Caleb, this is going to be cosine because, remember, this is the normal force, right?
Yeah.
That M1G cosine theta is our normal force. And so it's going to be 0.210 times 3,500 times 10, right? See how, like, if I wrote all this out, it's going to be like, wow, that's a lot of stuff, right? So 0.210, remind me to charge this. I'm almost out of battery.
Charge it when you're done.
I said, remind me later. That's something I would do to my wife, right? Can you remind me to order this? Hey, don't forget to order this. At least later. So our frictional force is 6,400 newtons, right? So I'm just kind of collecting all this together. So when I actually get like an equation, I can just plug in numbers instead of plugging in all the formulas, right? And so I do the sum of the forces, right, is equal to MTA, right, mass total times acceleration. What forces do I have acting? I have FG1X minus F minus G2. If you do a quick calculation, this is 16,400. This is 17,500. You would see that this is definitely bigger than this, right? That's the reason why it would accelerate down the incline. And that's going to be equal to MTA. And solve this for acceleration. So FG1X minus F minus FG2 over M1 plus M2, right? That was our MT. Right, and so for the teacher who does physics classroom, he kind of does what I did here. He collects all these numbers and then substitutes in. That's effective on a problem like this because, like, if I'm plugging in this, and that into that equation over there, or if I'm putting in the equations into the bigger equation, I take up a lot of space, right? And so this is going to be 17,500 minus 6,400 minus 10,000 over 4,500. And so what it boils down to, it's like 1,100 over 4,500. And so you end up with approximately, right, 0.24 meters per second squared. So note that it doesn't really accelerate at a great rate, but it does accelerate. So it'll be like, right? Okay. Now, which one would be the easier one to find the tension for? The hanging block, right? Because the tension, again, just boils down to be mass times G minus H. And so that's going to be 1,000 times 10 minus 0.24. And it's something like 9,800 or this will be, the way we have it written, it'll be 9,760. So we're getting more comfortable with this method, with this process, this technique. But I also do want to stress out, it's no different than it's not really different than what we did before. It's just less work, right? The process is still the same. It's still what? Draw, sum, solve, right? It's just the difference was when we did it as two systems, we'd have two equations and two unknowns, and we would combine them. Here we have really one equation, right? One unknown, and then we got to go back into this equation and find the tension. That's all it is, right? So it's not too bad. Okay. Now let's look at this next one. What happens when we have multiple force or multiple objects hanging off of an Atwood machine, right? A basic Atwood machine. Well, again, whole system and then break it down further. What happens is this tension and this tension are equal. This tension is not. Okay, that's its own tension, right? The way you think about, anytime you have multiple objects hanging off of something, the tension in the rope is responsible for what's hanging off of it, right? So for example, this block, right, the tension here is only responsible for that block right there. But this tension is responsible for what? Both of them. And this tension is responsible for
Is
that
the
big
way
one.
the pulley, like the pulley kind of looks like it divides the rope that is attached to 2 and 4.
That's just a picture.
Okay.
That's just a picture thing.
I know that, but is it actually treated like that?
So if you look at a
Does
pulley,
your rope
there's
teeth
a
wide?
if you look at a pulley, there's a groove. If you look at the physical pulley, there's a groove where the string sits on.
Yes, I know.
And so that's all. It's really just hiding right there.
I know, it's just you wrote T twice, and I wasn't
Well,
sure that was.
no. So if we're looking at this string here,
Yes.
right? The tension on the left equals the tension on the right.
Yeah.
Okay. And then this tension down here would be its own tension, right? Or let's call that T1 because that would be the tension. Whoa. That's weird that I did that. But that would be the tension, right, in the 1 kilogram block, right, if you want to say. That's what we'll call it T1. But the other ones are just called T. Okay? So, system. This one you have to be careful with, though, because sometimes you may forget that that 2 kilogram block adds to this system, right? But how many forces are acting here? How many blocks do I have? 3. I have to account for all the blocks, right?
Yeah.
What's trying to pull this system? This here, right? FG, we'll call it 4 because it's a 4 kilogram block. The 1 kilogram block, and then the 2 kilogram block. The only force that gets canceled out because they're truly inside are the tensions.
Could the Could the 1 and the 2 kilogram block not be treated as one system in a sense?
You could treat this as one system, which is it means it's a 3 kilogram mass hanging out there. You could do that. And so what happens is on the 2, now everybody's like, but wait, doesn't that other tension affect, right, everything here? So here, this tension, right, gets canceled by that tension there. But remember, this is also experiencing the T1 tension, right? And that's experiencing the T1 tension. Those cancel there, right? So internally, all those tensions still cancel, right? Even though that 1 kilogram block is kind of hanging out by itself, it's pulling on 2. So it's trying to pull 2 down with it in terms of the tension, but like it's pulling up on 1, right, on that little string. Okay. Sometimes you may get a question that looks like this, right? So it's kind of, this is an equilibrium problem, right? This has a tension up here, but you got to remember, this piece of the rope is responsible for all 3 pieces, right? All 3 masses. This one is only responsible for these 2. This one's only responsible for that one. Okay? All right, so let's do our free body diagram. We know we're going to have a total mass. Which way do you think this wants to accelerate? So if we treat this as a 3 kilogram mass, which way does it want to accelerate? Right? The 4 kilogram block wants to go down because there's only 3 kilograms on the other side. Okay? And so what happens is so FG4 is going to go up because it's in the positive direction, right? Because we're going to go in the direction of the motion. And you have FG2 and FG1. Right? So everybody got that? And so sum of the forces is equal to M total A. Everybody still with me? Good. And then we got FG4 minus FG2 minus FG1 equals M total A. I'm just going to kind of shorthand this a little bit, right? Each one of these is going to be mass times 10. So this is going to be 40 minus 20 minus 10 equals, our total mass is going to be 7. Because it's 4 plus 2 plus 1. Right? And so over here we have 10 equals 7A. So what does the acceleration equal? 10 sevenths, or 1.43 meters per second squared. Right? Giant red flag was what? Divided by total mass. Remember that 2 kilogram block's in the system, right? It's there. It's not like outside the system, it's inside the system. So we have to account for, or that 1 kilogram block, sorry. Right, it's in the system, so we have to account for that. Okay? Now let's find the tension in the string supporting the 4 kilogram block. So now I say, okay, what do I have acting on the 4 kilogram block? I have the weight of the 4 kilogram block, and then I have T up, right? And this wants to go down. So officially, when I sum the forces, it's going to be FG4 minus T equals M4A. But what happens again, I end up with T equals M times G minus A. I add T over, I subtract M4A over, right? And then I count for it there, right? So everybody got, so that's what you do, right? Add T, subtract M4 over, or M4A, and I get that T minus M times, or T equals M times G minus A. And now I just plug in, right? 4 times 10 minus 1.43 And so the tension is equal to, I didn't finish this part, 34.28. Luke, will you have to remind me to do later?
Charge your calculator.
Thank you. Yep, 34.28. So
Who
34.
is texting you every 30 seconds?
There's a group text between my wife and her friend.
They need to go back to work.
That's it. I'll tell my wife that you said that. Then you have to answer to her. All right, so now we just need to find the last part is to find the tension in the string connected to the 1 kilogram block. You could do this one of two ways. You can look at the 2 kilogram block, but again, we're going to find the simplest block, right? What's the simplest block? Go right to the 1 kilogram block, right? That's the easy one. I'll do it up here. So here's my free body diagram. I've got the tension in 1 up, the weight of 1 down. But remember, it's also being accelerated, right? So don't think it's just hanging out there by itself. It's being accelerated with the system. So we would have T1, and that's going to be positive, right? Because it's going to go up minus M1G equals M1. I'm writing over my little diagram there. Right, so M1A. Now, this tension is going to be a little bit different because of the way everything's acting here. This tension is going to be M1 G plus A. I feel like that was, yes, no, that's right. So it's going to be 1 times 10 plus 1.43. Which is just going to be, there we go, 11.43, right? Right, so this, I'm going to play like follow the arrow, right? That's going to be our answer to choice, or part C there. Okay? You guys remember this question on the test? There was, I think it was like question 1 or something like that. Or 2.
Yes.
This question.
No, I guess.
You guessed.
I know
I
what
heard
to
it
do.
about the 2 questions.
I feel like question 1 was harder than this one. Question 1 had like 3 on one side, and then like.
So if you have 3 on one side, right? Again, you just have to remember each part of the string is responsible for what's hanging below it.
Yeah.
Right? So this part of the string is only responsible for the 1 kilogram block. This part of the string is responsible for the 2 and the 1, which is the reason why this part is 34.3.
There was like another one where there was 3 blocks vertically, and you had to find one of the tensions of the strings in the middle as they were all being pulled in 2 different directions.